Okay, so as we looked at in another clip, we've defined hydrochloric acid, so HCl. We've defined hydrochloric acid now as both an acid and also a strong acid. And what we have said is this will give us a pH range, typically between 1 and 3, because it's a strong acid. And we know that this will be the case because we are undergoing complete dissociation of every single one of the HCl molecules that go into solution. And so if that occurs, we can define our HCl as a strong acid because we get complete dissociation to produce what we now regard as the important part of an acid, the H plus ion, in order for HCl to donate that proton to something else, typically an alkali or a base. Now, when we've been talking about these things, we've always been giving these a pH range. We're always saying it's between 1 and 3 or 4 and 6, something like that if it's a weak acid. And this has to come from somewhere, and indeed it does. If we are using a 0.1 molar solution, by that what we mean is if we take 0.1 moles of HCl and we dissolve that into 1 litre of solution, we get a 0.1 molar solution. That will give us complete dissociation and will produce 0.1 moles for every litre of hydrogen ions. That will give us something of a pH of 1. There's a numerical calculation which you can look for, which allows us to do this. If we were to change this concentration and use 0.01 molar solution, we would get a different pH. It's still a strong acid, it's still undergoing complete dissociation, but if we've got less moles dissolved in 1 litre of solution, we have less hydrogen ions in solution. So it's still a strong acid, however the pH value will change. And actually what we see is if we change the concentration by a factor of 10, we change the pH number by 1. So if we went to a 0.001 molar solution, that would then give rise to a pH value of 3. And so you can use pH numbers and vice versa concentrations to predict one or the other way around, because we know that a tenfold change in concentration leads us to a unit change in pH. It's a logarithmic scale. And when you do A level later, pH numerically is found to be the log to base 10 of the actual hydrogen ions in concentration in solution. And so you can see from there that if we'd had a comparatively weaker acid, such as ethanoic acid, and which doesn't undergo complete dissociation, the concentration of the hydrogen ions would be subsequently even lower because they haven't dissociated all those hydrogen ions, and so the pH would be even lower. And then what we can see is we're moving then towards a pH of 4, 5, and 6 because the concentrations of these values are even lower because they haven't dissociated. But we can use the pH numbers to predict a concentration of a strong acid, or we can use the concentration to predict the pH value if we know one or the other. This works with strong acids. We're not going to try and do it with weak acids at this stage, but it will definitely do it with strong acid when you're undergoing complete dissociation.